Welcome to the investigation for differentiation rules. So we're going to start with this first box here. We're going to find the derivative of y equals x cubed. If you remember from our investigation several months ago, the derivative is basically the slope or the gradient of the original function. So in this case, the original function is y equals x cubed. It's a cubic function, which looks kind of like this. If you don't remember, let's look on Desmos here. So there in blue is the cubic function. So we're going to measure the gradient or slope at different points, just like we did in the investigation for the mosaic investigation a couple months ago. So I'm going to do it for several points here, 0.5, 1, 2, etc. And then I'm going to fill in the gradients here. If you remember, we did this exact same thing, but just to review, we're going to go ahead and do it again. So I built this little manipulative, which draws a tangent line at different points on the blue curve. So I'm going to first measure the tangent line at x equals 0. So I'm just going to type in x equals 0. And you can see that it's a flat line. And so the derivative at that point is basically 0. My manipulative actually measures the slope of this little triangle here, so it's not exactly 0, but theoretically it is 0, it's flat. So I would write in my table here, which has the x-coordinate on the left and it has the gradient on the right, I'm going to write down that the gradient is 0, okay? What about at x equals 0.5? What is the gradient at x equals 0.5? So now I'm going to type in 0.5. I'm sorry, 0.5, this Brazilian keyboard. And so this gradient appears to be 0.75. So I'm going to type in 0.75 here. 0.75. And I'm just going to turn this off. This is distracting. And then I'm going to go and do x equals 1. So I'm just going to do this for several different points. At x equals 1, the slope is 3. This manipulative draws a little slope triangle here, and it measures the actual gradient of this tangent line. So what about x equals 2? The gradient is 12. Okay, and then I'm going to do it for some negative values. So I'm going to do it for negative 0.5, negative 0.5, and oops, equals. The gradient is 0.75. So I'm going to put 0.75 here. And then finally, negative 1. And so this gradient's 3. It doesn't say exactly 3 because my manipulative is actually drawing this little triangle, but theoretically it's 3. And finally, x equals negative 2. And this slope is 12. Okay. So now what I'm going to do is I'm going to turn off my original blue function. I'm going to turn off the tangent line, and I'm going to turn on the points that I just collected here. And look, it forms a parabola, doesn't it? And it turns out that the equation of this parabola is not x squared, because it's vertically stretched. How much is it vertically stretched? Well, let's see. Is it 2x squared? No. Is it 3x squared? It is. So it turns out that the derivative of y equals x cubed is 3x squared, which is called the power rule. Do you remember the power rule? You take the 3, you bring it down in front, and then you reduce the 3 by 1, and you get 2 in the exponent. Okay, that is the power rule. By the way, let's fill in some of these values. So for x, I use 0, 0.5, 1, and 2. For 0, the slope was 0. For 0.5, the slope was 0.75. For 1, the slope was 3. And for 2, the slope was 12, right? I'm not going to write them all down because it's repetitive. But so the shape of the derivative function is a parabola. And the function is y equals 3x squared. And you can find it by using the power rule. If you remember, the notation for derivative is y dash, or y prime. What is the derivative of y equals 2x cubed? So if you have a 2 in the front, that is a vertical stretch, right? Let's take a look at 2x cubed. Okay, so here's 2x cubed. I'm going to turn off some of these extra. Okay, so here is y equals 2x cubed. It's a stretched version of the original curve, right? And I'm just going to measure the derivative at different points like 0, 1, and 2. So, of course, at 0, it's still 0. Let's turn on the tangent line. So you see that the slope is actually 0 at 0. So I put 0 here. And at 1, at x equals 1, the derivative is 6. And the derivative at 2 is 24. Okay, so you can see that what happens with this is it is much steeper than it was before. Let me just turn on, I'm gonna turn off my original function. And I'm just gonna leave the points that I graphed here. Look how steep this is now. The original point, remember, was 1, 3. This one is 1, 6. 1, 6. So actually this derivative function is twice as tall. Does that make sense that if I make the original function twice as tall, that the derivatives, the slopes along the blue function are also twice as big? Okay, so that tells me that if I say, what is the derivative of 2 times x cubed? I know that the derivative of x cubed is 3x squared. The derivative of 2x cubed is going to be 2 3x squared. So it's going to be 2 times 3x squared, or 6x squared. And that's called the coefficient rule. If I have a coefficient here, when I take the when I have a coefficient here, when I take the derivative of it, the coefficient remains there, because a function that is vertically stretched also has slopes that are vertically stretched. Okay? All right, let's go to the second box here. I'm going to move this to the side. Now we're going to work on the derivative of y equals sine x. Okay, so we're going to do the exact same process. We're going to check, oh, by the way, the points that we measured dy dx at, we did it at 0, we did it at 0.5, we did it at 1, and we also did it at 2, right? Here, we're going to do the same thing with y equals sine x. If you remember, y equals sine x looks like, I should do the original function in blue, because that's the color it is in the Desmos. So y equals sine x looks like this. We're going to find the derivative at certain points on this graph. Definitely here, definitely here. We're going to maybe find some points here too, and we're going to write them down into our table here. Okay, so we're definitely going to do it at 0. We're definitely going to do it at pi over 2. We're going to definitely do it at, I'm sorry, this is pi, not pi over 2. And this is pi over 2. And this is pi, okay? So let's do that. Let's go to our Desmos and we'll open up sine x. Here's our sine x. And we're going to find the derivative of different points here. First, we'll start at 0. So I'll put 0 here. And the derivative at 0 happens to be 1. How interesting. Okay, and let's try it at pi over 6. Pi over 6, remember, is 3.14 divided by 6. This Brazilian keyboard. Okay, so the derivative at this point is 0.866. And pi over 4. Pi over 4 is 3.14 divided by 4. So the derivative is 0.707. And pi over 3. Pi over 3, the derivative is 0.5. And pi over 2, the derivative is 0. And 3/4 pi, the derivative is negative 0.707. And the derivative at pi is negative 1. Okay, so now let's turn the original function of the tangent line off. And let's turn on the points that we just stored in our table. What does this look like? It starts at 1 and it goes down. And at pi, it's negative 1. What does this look like? Doesn't it look like cosine? It is cosine. So it turns out that the derivative function for sine is cosine. Let's fill in some more of our table here. So we put in some of the x values here into our Desmos graph, and we found out what the derivatives were at certain points. And at 0, the derivative happened to be 1. At pi over 6, the derivative happened to be 0.866. Let me click on this so that you can see the numbers. I'm just copying these numbers here. At pi over 4, the derivative was 0.707. At pi over 3, the derivative was 0.5. And pi over 2, the derivative was 0. And at pi, the derivative was negative 1. And from this, I found out that the shape of the derivative function was y equals cosine x. It was another trig function. Y dash, the derivative of sine x is cosine x. Okay, let's go to the third box. Find the derivative of y equals natural log of x. Oh, in case this was covering it up, sorry. So all I did was I wrote what the shape of the derivative function is a trig function, and the function itself is cosine x. Okay, let's go to the third box. Third box, we're going to natural log. Okay. So we're going to do the same thing with the natural log function, and we're going to put in a few different points like 0, 0.25, 0.5, 1, 2, 4. So we're going to put in 0, 0.25, 0.5, 1, 2, and 4. And the natural log function itself looks like this, right? And the places we're going to check are 1, 0, 0.5, 2, 4. Okay, so those are the places we're going to check the slope of. You can see that at the beginning, the slope is very steep. And then as we go along, it gets less and less steep. Okay, so we're going to see that on these values here. So if we put in x equals 0, we'll see that the derivative is infinity. Okay, and at 0.25, the derivative is 4. 4. And at 0.5, the derivative is 2. And at 1, the derivative is also 1. And at 2, x equals 2, the derivative is 0.5. Oops, 0.5. And at 4, the derivative is 0.25. Okay, now I'm going to turn off the original function and the tangent line. And then I'm going to leave on these points. So these points are the derivative points. Do you notice a relationship between the x's and the derivatives here? 0.254, 0.52, 1, 1, 2, and 0.5, 4, and 0.25. Remember, 0.25 is 1/4, 0.5 is 1/2. Do you see the relationship? 1/4, 4, 1/2, 2, 1 over 2 corresponds to 2, 1 corresponds to 1, 2 corresponds to 1 over half, 1 over 2, and 4 corresponds to 1 over 4. Yeah, it's the rational function. It's the inverse function. We worked with this a bit in chapter 2, right? So the derivative function of natural log is 1 over x. So it's a rational function. And the equation is 1 over x. Okay? So there's a reason why we use log base e, right? Log base e is kind of a weird number, right? The e is like 2.718 and it goes on forever. Why on earth do we use natural log like it's something special? Well, the derivative function of natural log is exactly 1 over x. So that's really nice, right? If it was log base 10 or anything else, it would not be this nice. Okay, so that was box 3. Now 4. So box 4, what we're going to do is we're going to now find the derivative function for 2 functions that we know how to take the derivative of separately. So remember, we know how to take the derivative of just sine x. It would be cosine x. We know how to take the derivative of 0.5x using the coefficient rule and the power rule. We know that that is 0.5 times 1, or 0.5. So, but what is the derivative of both added together? Okay, so remember, sine x is this function here. And 0.5x is a line that has about this slope. If I add these 2 functions together, I'm going to get a function that is a sine function, but it's just going to go up and up and up, just like this pink line does. So the pink line makes the original blue sine function kind of tilt upwards. So what I'm doing here is I'm going to have the derivative of the pink function, which is this pink triangle, and the derivative of the blue function, which is this blue triangle, and I'm going to add the two triangles together. So I'm going to have the pink triangle and then the blue triangle kind of mashed on top of it. And what happens is the amount that the blue triangle goes up is added to the amount that the pink triangle goes up. So when I find the derivative of the two functions added together, all I need to do is take the derivative separately and add them together. So the derivative of sine x plus 0.5x is cosine x plus 0.5. So that's very handy because now if we ever see two functions added together, if we know how to take the derivative of each function separately, we know the derivative of both added together. Okay, so let's see. We're going to test this out, but the derivative of sine x, of course, is cosine x. The derivative of 0.5x is 0.5. Now let's test it out. We're going to find some values. So we're going to find the derivative of sine x at x equals 1. We're going to find the derivative of 0.5x at x equals 1. And then we're going to use the Desmos manipulative to find out if the derivative of the combined function is equal to these two added together. So let's see. So we already have a Desmos manipulative for sine x. So let's find the derivative of sine x at x equals 1. We find out that it is 0.540. Okay, so the derivative of sine x is 0.540. What is the derivative of 0.5x at x equals 1? Well, remember, this is a trick question. We know that the derivative of 0.5x is 0.5, and it's always 0.5. It doesn't matter what x equals, so it's actually equal to 0.5 all the time. If we add these two together, which is what we think the derivative of the two separately is, we would get 1.04, right? And let's test to see if that's correct. Let's make a manipulative, which is sine x plus 0.5x together. There it is. This is the function sine x plus 0.5x. Let's find out what the derivative is at x equals 1. It's 1.04. So it is 1.04. Okay, so the derivative of function, So the derivative of function f plus function g is the derivative of each of the functions separately added together. Okay, so the derivative of sine x plus 0.5x is cosine x plus 0.5. Notice cosine x is the derivative of sine x. 0.5 is the derivative of 0.5x. Okay, that's it.